right, welcome to video 5A. Evidently, I can just slap A's or B's on the end of anything and make them a new video. But today we're going to be talking about heating curves and specifically how to calculate the overall change in energy when some substance goes through a change of state as it increases temperature. So let's jump right to our note pack, which is page 18. And essentially what we're going to be doing today is we're going to be trying to show how substances change state as they're either heated or release heat by using the heating curve. Now, every single heating curve that we're going to have has two parts: when the temperature is being raised and when we're breaking intermolecular forces. So what you should be aware of is this: whenever something either freezes or melts, which is kind of the opposite of each other, or if something is boiling or condensing, in both these cases, what's happening is intermolecular forces are being broken. You may not be aware of this, but if we have an ice cube at zero, so let's say we take an ice cube and we put a flame underneath it. So this is my flame, clearly, and we're heating that ice cube up. When it hits zero, that ice cube's temperature will not increase above 0 degrees Celsius until it's completely melted. In other words, all the intermolecular forces that are very tightly attached to each other in a solid until they break into a much looser liquid form. And then they can increase temperature again. And then once again, when you hit the boiling point, so now we're keeping it in a pan of some kind, we still have the same wonderful heat source underneath. And now we have liquid water. But when we hit 100 degrees Celsius, the temperature will not change until every single one of these water molecules has broken apart from its intermolecular attraction and left. So you can probably understand this as kind of a corollary. The greater intermolecular attraction, the higher your boiling points are going to be, because it's harder, it requires more energy to break these things apart. But what's really crazy is that you can be heating for a long period of time and not see your temperature increase. Why? Because changes of state require a great deal of energy to break apart intermolecular attractions. It's easy to see when energy is being applied when the temperature changes, because there's a correlation. You add energy and the temperature changes. So here it's kind of cool if you take a look at a thermometer and you see my drawings are absolutely horrible today. This is a thermometer and it has markings, right? If you add heat to this, the temperature is going to go up, right? So when we see that the temperature going up, we know that energy is being applied. But energy can also be applied consistently and not have the temperature change. And the best way to understand that is by looking at a heating curve. Now, this is an example of a heating curve, and I want you to take a look at it in your notes. And this is exactly what we're talking about here. Here's where the temperature is being raised, and here's as we're adding heat over time. Now, this graph talks about time, but we could also have this graph be written as energy. So as we're adding in more energy, but it kind of goes without saying, as time passes, you're adding more energy as well. So they sometimes go back and forth, these graphs. So it doesn't matter what substance we have. Do you realize that every single substance has three states: solid, liquid, and a gas? Below the solid liquid phase, we can use Q equals MC change in T to figure out the amount of energy or the heat that's being applied. So this formula right here, Q equals MCAT, that's being used whenever we have a change in temperature. And that's really important here, because if this formula only works when there's a change in temperature. But when we hit the point, so let's say we have some sort of solid right here, right? And again, we're heating it. That's a candle, right? We're heating it. And the temperature goes up over time until it hits whatever the melting point happens to be of that particular solid. When it hits that melting point, we're still adding energy in, but we cannot use the Q equals MCAT equation anymore, because there is no change in temperature, which means if we put a zero in here, then if we use this equation, we'd say, there's no more heat that's being gained or lost. So we have to use a new equation, and that's this one right here, and it's Q equals M times the change in H. And this change in H is a constant, and it's usually either the heat of fusion or the heat of vaporization, and that's a specific number that correlates only when you're at a change of state. So for example, here we're changing from a solid to liquid. Over here, the instant that we hit this melting point, the intermolecular forces start breaking, and all the way through to right here, we're applying energy into here, right? So that is where we use this equation. So we use Q equals MCAT right here. We use Q equals MH right here. And if you see here, we say areas 1, 3, and 5. So 1, 3, and 5. Do you see where we have temperature raises in all of these three places here? We can go ahead and use our good old Q equals MC change in T to figure out how much energy is being put in. Oh, by the way, this is really, really important. We're putting energy in here to cause the solid to become a liquid and then become a gas. If we were reversing the process and we had a gas at the start, we'd be actually releasing energy to become a liquid and then to become a solid, because that's how it works, right? So it's also important because whenever you're going one direction, all of the energies are going to be the same sign, because remember, sign impacts our energy change. So if we are adding energy in, which we're doing all the way in all these steps here, all of these energy changes, all of these Q values are going to be positive. If, however, we were going the opposite direction, all of them would be negative values. And that's tricky because when you do our change in T, which whenever we have a Q equals MC change in T, our change in T is always final temperature minus initial temperature. Now you can probably do the math here and realize that if we're going up, that means that our change in temperature is always going to be positive. But if we're going down, that means that our final temperature will be lower, which will end up with a negative value. And that's tricky because then we'll end up with a negative Q. But if we're going down, that means we're losing energy. Well, negative signs means that you're gaining or that you're releasing energy, and positive signs mean that you're taking in energy. So you have to kind of assume this. Whenever you're going one direction on a graph, all of the signs are going to be the same for your Q, regardless of whether or not you have positive or negatives when you're doing your math. Now, how does this work exactly? Well, the best way to do this is do a problem, but you can find tables where every single element or substance has a specific heat of fusion. And that's when you are either going from a solid to a liquid or a liquid to a solid. And they have a heat of vaporization, which is when you're going from gas to a liquid or a liquid to a gas. The number does not change whether or not you're going in either direction. So the best way to do this is to actually do a problem. And so I wrote this problem really, really quickly, and I realized after I did it, the problem is just so flawed. So let me write a couple pieces of information here that you really need. One, I did not tell you in this problem how many grams of ice we're starting off with. So that's the biggest fail. You can't solve this problem without knowing that we have 10.0 grams of water. The second thing I want to change here is this, because I want to make this a problem that's going to be representative of how you might find it on the AP exam. I don't want to stop at 100. I want to stop at 120 degrees, because we know that at 100 degrees is when water changes state from a liquid to a gas. So I didn't want to get right to that point and then not worry about calculating out the temperature change. So we've been given in the problem, we've been given the heat of fusion, and that's the change in H that we're going to use. And I'm going to put this on our side here just so we have it. The two equations that we're going to use throughout this problem are Q equals MC change in T, and that's whenever we have a change in temperature. And the other one is going to be Q equals MH. And what we put here is either going to be an fusion, or it's going to be Q equals MH vaporization. It depends on whether or not we're, because the constants change whether or not you're going from a liquid to a solid to a liquid versus a liquid to a gas. So I like to break things down just like we did. You notice how we, in this particular diagram right here, they broke things down into parts. And at first, and if you take a look at the actual mathematics here, you're going to see how we're starting at minus 20. So let's pretend that this is our 0 mark, right? And we're starting at minus 20. First, when we go from minus 20 to 0, won't we be changing temperature for water? But then at 0, won't we stay at 0 until we break all the intermolecular attractions? And then once again, once we jump up from 0 to 100, and then at 100, won't we stay until we break all the intermolecular attractions? And then we jump from 100 to 120. So what I'm going to do is I kind of broke this up into this, and this is how I actually, when I solved this on my own, I kind of drew it like this one. I went, all right, these are the parts that we're going to have to solve. We're going to go from minus 20 to 0, right? And then we're going to have to go from 0 to 0, right? Just stays there. And then we're going to have to go from 0 to 100. I don't know why I wrote 110. And then we're going to have it stay at 100. And then we're going to have to go from 100 to 120 degrees Celsius. Also, as I looked at this problem afterwards, I did not do any justice to significant figures here. Let's pretend that everything has 3 sig figs, even though I've not done it correctly. So what we know is this. In each of these little spaces here, we're going to have to solve for the amount of energy that's being inputted to make that change. So if the temperature is changing, we're going to use Q equals MCAT. So I wrote underneath each one of these here what's happening in each of these. So if we wanted to, we could say this is 1, this is 2, 3, 4, and 5. These are the five different times that energy are being applied to our piece of ice. So for number 1, we could say, well, we're going to use Q equals MC change in T. And we're going to have to add that to our number 2. And in this case, it's going to be Q is equal to M H. And we're going to use the fusion constant, because fusion, think of something as fusing is when something turns to solid. So when something's turned to solid or vice versa, we use the term fusion. So this is the equation we're going to use for that. Plus, we're going to go to step 3, which is again 0 to 100, and that's where the temperature is changing again. So we're going to go Q equals MC changing T for that. And then for number 4, we're again at a place where the temperature is not changing, but in this case, we're going to have to use a different heat enthalpy. It cannot be the heat of fusion. We're going to have to use the heat of vaporization, because that's the constant that we use whenever something is going from liquid to a gas or vice versa. And then finally, in step 5, we're going to add in our, again, going from 100 to 120. So that's going to be Q equals MC change in T. So in all these cases here, what we're going to do is we're just going to plug in numbers. So if I go over here, I'm going to go 10.0 grams, and I'm going to use the specific heat of water. By the way, I did not include the specific heat of water in here. They kind of expect you to know it's 4.184 joules per gram degree Celsius. That's the specific heat of water. They might give it to you in the problem. In fact, they likely would. So 4.184 joules per gram degree Celsius. And then the temperature change here, wouldn't it be, the final temperature be 0 and the initial be minus 20? So wouldn't that be 0 subtract minus 20, which wouldn't that be 20, right? So we have that. Then we're going to add that to our mass, which happens to be 10.0 degrees, right? And we're going to multiply that by 334, right? And we're going to then add that to Q equals MC change in T, which again is going to be 10.0 times 4.184. That does not change throughout, if you notice here. And I've gotten lazy with the units. Please forgive me for that. It should be grams right here, and this is a 10. And this should be, if you take a look here, joules per gram. So the grams cancel here. 4.184 joules per gram degree Celsius. And then our change in temperature in this case is 100 degrees Celsius. And then finally, in our step, we go 1, 2, 3. When we hit 100 degrees Celsius, we have our mass is still 10.0, because the laws of the universe stay the same. And now our heat of fusion is, vaporization is 2230, which is a crazy number, right? So we're going to go 10 times 2230 joules. And then our last step, 5 here, we have to add in Q equals MCAT again. And I want to point out something to you here. Do you see how when we go from 20 to 0, it's the same temperature change as 100 to 120? So wouldn't it be exactly the same value as this right here? But we're going to write it in here anyway, 10.0 grams times 4.184 joules per gram degree Celsius. All of that times 20. Now, I did the math in advance on this, and I got 836.8 joules here, which, not surprisingly, over here we get 836.8 joules. Here, when we multiply 10 by 334, we're going to end up with 3,340, which kind of is a big jump in energy from here to here. And then here we get 4,184 joules. And then here we end up with 22,300 joules. So I'm going to put the numbers in here like this, and these are all the numbers that we are adding together. And when we add them all together, when I did this, I failed to take into consideration that I had made a mistake with my numbers here. And so the actual number I end up with here, joule-wise, is 31,497.6 joules. Now here's the thing, the joules are really, really tiny numbers, so they hardly ever want us to use joules as our final answer. So what we end up doing is we typically convert that to kilojoules. So if I were to convert this to kilojoules, we just take our number right here, right? And as we all know, there are 1,000 joules for every 1 kilojoule. And if we do the math on this, that's going to end up with what? 31.5 kilojoules. So what we've done is we were able to walk ourselves from the bottom with a solid all the way up to a gas, calculating out the energy changes all the way through. And this is a problem they typically like. Again, all of these signs here were positive, so we were putting energy in to cause the temperature to raise and also to break the intermolecular attractions. If we'd gone the opposite way, the reaction would have indeed been negative the whole way back. Instead of putting energy in, we would have been releasing energy the whole way. Anyway, we'll see you in the next video. Hopefully this helps. Thanks. Bye.